we continue to discuss the property of graph-based search. Basically, we can divide the graph structure into 4 different types. Okay, so we call it 4 base graphs, A, B, C, D. So the basic graph is usually too slow or too dense. So based on it, there are some algorithms you can see later. There are some algorithms based on these basic graphs, basic algorithm, to try to improve it. Here you can see the roadmap of how they develop their algorithm based on the 4 different base graph structure. Okay, so let's briefly review these structures. Okay, so the basic principle is the graph should not too dense. If it's too dense graph, too many connections between nodes, it will make your search slow. And so we hope it's moderate dense. But you should make sure that each point is reachable. You can from one point to any of the points. You should make sure it's reachable. Okay, let's see the first one. It's called a dynamic graph. And the dynamic graph is you can reach the correct answer. Okay, but its connection will be too dense. Okay, so it's called a dynamic graph like this. And for example, its degree is its degree. The connection in total is 40. You can see it's very dense graph. Okay, the second is called RNG. RNG, its full name is relative neighborhood graph. Okay, so the idea is this. You can see the degree is less. It's only 24 degrees in this graph. And then you see the connection is sparse. Okay, it's more sparse than the DG. And the main idea is if we, based on this, the X and Y, we hope during the X and Y we can draw a region called a rune. And during this rune, there should be no ending points in this region. Otherwise, they should not build a connection between X and Y. So it's a basic idea called you should not have any points during this rune. Otherwise, you should not build a connection between them. So we will address beside what is the idea. We will address it later. And the third graph is called a k-nearest neighbor graph. A k-nearest neighbor is we will limit for each node. We limit how many neighbors. For example, maybe 2 or 3. Okay, so for each node, at most 3 neighbors. So it's called a k-nearest neighbor graph. Okay, so k at most. So try to enforce the sparsity. But this graph cannot guarantee your connectivity. Okay, so for example, maybe this one is very weak. Only one edge connect to the other subgraph. So if this edge is broken, we will separate them into 2 subgroups. The next one is called MST, the minimum spanning tree, called MST. You can see its degree is the smallest for these 4 base graphs. And the minimum spanning tree just can ensure your global connectivity, and its degree is very low. Okay, but it's lack of some shortcuts, so you should add some to improve it. You can add some shortcut between them. Okay, so here, based on these 4 base graphs, here is a roadmap to develop during the past years. You can see so many algorithms based on the graph-based structure. Okay, it's a lot of algorithms, but the basic structure is the same. Okay, we want to design a good graph, and then with the bin search to apply the bin search in your graph, and your graph should be moderate dense, so it can keep it accurate enough, but also have a good speed. Another issue is maybe we can also consider what is our start point, our entry point. Okay, so the initial seed may sometimes is matters. Okay, so for example, if our query here, if we always start from this entry point, so you need to take 1, 2, 3 to find your neighbors. But how about if we have another entry point? Starts here, okay, just one jump, you can reach your nearest neighbors. Okay, so such idea is maybe sometimes we can start our search from a good seed. It means you have a shorter pace and faster search. Finding a good seed is also like an ANNS problem, but it should not take you a lot of time to choose which seed you want to start. Okay, so you can use some simple structure like by using a tree, or use the hash function, or LSH. Next, we talk about how to prune your edges to make your graph not too dense. Okay, here are some cases. Okay, so give a new node want to insert in this graph. So what edges we should build for it. So if we find all its neighbors, suppose if the range during this range, or we consider all this range in the distance in some threshold. Okay, if we connect all the neighbors and connect with the edges, so you see this will be too dense. It will make your graph too complicated. Another way is, okay, maybe we just choose top K. For example, just choose top 3. But unfortunately, in this case, your top 3 only choose the top regions neighbors. But for the bottom regions, they are not reachable because you don't build any connection between these. Okay, so this is a problem if you say only top K can be connected. Sometimes it will cause this problem. The accuracy will be not very good. Okay, so that's why we propose, we will introduce the RNG pruning. So RNG pruning can try to create a moderate number of edges. Now, not too many, but not too few. Okay, like this. So you will connect some connection to the top region and some connection to the bottom region. Okay, so here is the idea. What is the RNG pruning? How they do it? Okay, so here, give an example. We give a node A, and we want to make an edge with its neighbors. All are the neighbors of A, but not all neighbors have to create an edge between A. Okay, we can choose it. how to choose? Okay, so first we find the nearest one to A. Okay, so in this example, node C is the closest one. Okay, so we just build a connection between them. Okay. So here we build a real connection between A and C. And then we find the second nearest to the node A is node B. Okay, so should we create an edge between A and B? Okay, we have to consider if B is also a very close node to the A's neighbor. Okay, so here the green line indicate we should calculate when we find is consider the node B. We should also consider the distance for node B and the A's neighbor. Now C is A's neighbor, right? So we consider the distance between B and C. Okay, you see the distance is very short. It's shorter than the distance to AB. So in this case, we should not make an edge. We just keep them empty. No edge between A and B. The intuition is okay, since B and C are very close, so maybe they already have an edge between them. Maybe. But it's not 100% sure. But we just guess, maybe they have an edge between them. Okay, so we don't need to create an edge between A and B. If they, because B and C are very short, their distance short, so we suppose they already have an edge. So we can use from A to C, and C can reach B. We assume that. So we don't need to make an edge from A to B. So it's an intuitive idea why we discard the edge between A and B. Okay, any problem? And let's take the third nearest one is node D. For node D, okay, again, we compute the distance between A and D, and also compute the distance between A's neighbors. Currently, you only have one neighbor, C. Okay, we compute the distance between CD. Okay, CD's distance is longer than AD. Okay, so this means we can keep AD. So we make an edge between them. And the last one is node E. Okay, so apply the same procedure. We compute the distance with compute the distance between E and the A's neighbor. A currently has C and D are A's neighbor. So we have to compute the distance between CE and DE. Okay. Okay. From this, we find DE is very short. It's the shortest distance and shorter than AE. So based on our assumption, maybe they already have an edge between them. So we don't need to make an edge between AE. So we don't make an edge. Discard this edge between AE. So this idea is called RNG form. Okay, any comments? So it's a very effective edge forming technique when you build up the graph structure. And the implementation is easy, but it also requires many distance computation during this construction.